On Friday, I kind of went over how we transfer heat from one object to another and how we can actually calculate that. It's going to be pretty useful in the next lab that we're going to do, which is going to specifically ask you how to find the temperature of a flame. Now, most of us probably say, well, just stick a thermometer in there. We can't do that because number one, the thermometer is going to burst. So instead, what we use is a little bit of thermodynamics to help us find an unknown. So essentially, the way the lab works out, and you'll see this on Monday, but you're going to have basically, you have your ring stand, and on this ring stand, you'll have a piece of wire. Attached to that wire is going to be a nut, right? Just similar nut that you buy at like um at the hardware store or something like that, and it's going to be made out of zinc. I'm going to show you real quick how this works out. Oh, if I can draw a hexagon, that'd be great. Let's see, like that. That is an ugly hexagon. Let's try that one more time. One last time. Oh my goodness. Like this, like this, like this. Obviously, geometry was not my strong suit. Okay, whatever. Pretend it's a nut. All right, so you're gonna have the flame, all right, and the flame is basically gonna be transferring all of its energy to this nut that's at the end of this wire. Now, after it's been there for like 5 minutes or so, we're gonna let it rise to some temperature, right? The idea being is that whatever the temperature of this flame is down here is going to be the same temperature as the bolt up here, right? And that's what's going to enable us to find actually what the temperature of the flame is, because we're going to use calorimetry or heat transfer to find out how much energy was actually transferred into this nut. So over time, after the 5 minutes are up, what we're going to do is we're going to take this fire away. And now what we're going to do, let's actually make this black. Now what we're going to do is we're going to take the nut at the end of the wire, and we're going to put it in what we call a coffee cup calorimeter. Basically, all that it is a styrofoam cup filled with water. And we're going to measure what the temperature change of this thing actually is. We'll have a thermometer or something. The idea is that whatever temperature, whatever energy is exited out of the nut, we'll be able to measure. And if we can measure that, then essentially we can figure out how much energy is being exchanged from the nut to the water, which will enable us to go backwards and actually figure out what the final temperature, what the initial temperature of this nut was. Because over time, what's going to end up happening, and we'll learn this in thermodynamics, is the nut and the water are actually going to be the same temperature, meaning that they've reached what's called thermal equilibrium. So that's kind of the idea of this problem. So to kind of work you of how this kind of works out, I'm going to kind of give you a little bit of insight into how we're actually going to do this. So first and foremost, we're going to use the same equation that we had used before, which is the heat transfer equation, which is to say heat is equal to mass times specific heat times change in temperature. But I'm going to change this up a little bit. Instead of writing delta T like we normally do, I'm not going to give you the change in temperature because this time we're actually going to get it experimentally. So I'm going to erase that out. And instead, I'm going to break this apart a little bit, and I'm going to put T final here minus T initial. I should have made this a fancy T because that's like time. There we go. That's better. Because we're going to find both of these values actually experimentally. Of all these things here, everything is going to be able to be found experimentally, including how much heat was being transferred out. So let's take a scenario in which we get data that looks like this. So just like when we handle the problems on Friday, we're going to do it the same way. We're going to have our heat, we're going to have our mass, our specific heat, and our change temperature. This time I'm going to write T final, and I'm going to write T initial, just like that. But equals, 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 equals. All right, and now this one is going to be specifically for the water system. So I'm going to put water up above because we're going to denote each one separately. Like I said, we're going to do more of this when we get to thermodynamics, but this lab specifically wants us to do this. All right. So from the water component, it's going to be pretty easy. What we're trying to figure out for the water is we're trying to figure out how much energy was actually exchanged from the nut to the actual water system. Okay. So most of us are going to have the same mass. Let's say for the point of this problem right now, we're going to say that it's 100 grams, right? Or we measure that 100 milliliters, remembering that water has a density of 1, which means that whatever it is in milliliters, it's the same, the mass of it's the same in grams. So if 100 milliliters, it's going to be 100 grams. Because we know that it's water, distilled water, we're going to say it's 4.184 joules per gram degrees Celsius. Okay, so this is our units for specific heat. All right. And let's say we put this bolt into the water. Let's say it raises the temperature of the water to like 47 degrees. Now, your data might be different. This is just as an example that I'm using right now. So our data might say it's 47.0 degrees. That's what temperature it got to, right? And our initial temperature, let's figure it's like room temperature. So let's say like 22.0, just to make it easy for us to calculate. All right, so we have everything that we need, right? And like I told you guys the other day, when we're doing any kind of scientific problems like this, the way that I always handle it is I always write down everything that you know, and you can figure out what you don't know. So in this case, what we don't know is how much energy is being exchanged into the water. And as we talked about the other day, the reason we know that is because the change in temperature is going to be positive, meaning that the energy here is going to be going into the system, meaning that it's an endothermic process. So let's go ahead and calculate that now. So we're going to do my favorite thing in the whole wide world, which is to plug and chug. So we're going to get Q, in this case heat, is equal to 100 grams, point zero, don't forget your sig figs, times 4.184, times, now you can subtract it afterwards, or you can subtract it right now. Punch however you want. So I'll put it like this for right now. So 47 minus 22. It looks more like a multiplication. Minus, there we go. Okay, so now what we're going to do is we're going to take all these values and we're going to put it in our calculator. Let me pop that sucker out for just a minute. Oh, I forgot my numbers. I think it was 100 times 4.184 times, and this is when we do my calculator, I'll put a parentheses there. And I know that it ended up at, what was our value at again? 47 and 22. So 47, which is our final temperature, minus our initial temperature, which is 22. Now, if you have a scientific calculator, you can just punch this all at one time, but don't forget, it's very important that you put them in parentheses, because if not, then your calculator is going to do all the other work first. So you want this to happen first, your subtraction. Okay, so I hit equals, and I get something like 10,460 joules worth of energy. So now that I'm done with the calculation, right, I say that Q is equal to, oh, I forgot the number already. How many sig figs? Three? Three sig figs. So we say that it's equal to, let's say, 10,500. You can also write that in scientific notation. So we would write it as 1.05 times 10 to the 1, 2, 3, 4 joules worth of energy. Okay. So now we have to ask the question, okay, well, what is that 10,500 joules of energy actually represent? Well, what it represents, that's the amount of energy that actually transferred from our bolt to the water. Okay, this is going to be very crucial. So hopefully we got a very accurate number here. This part's probably the most important part of this whole lab. Seeing how much energy was actually transferred out of the bolt or the nut and into the water. And this is what it is. Okay, now question then becomes, okay, well, what are we going to do with this number? Now, don't forget, initially, what we're trying to do is we're trying to figure out exactly what the heat, or the temperature of this flame is. So we're using calorimetry, it's specifically thermodynamics and conservation of energy, to be able to figure out what our temperature is. Okay, so we're going to handle this problem exactly like we handled the water problem, except now we're going to have a new system. So let me make this a little bit smaller, so it's kind of out of the way. There we go. Make it a little bit smaller. Talking you guys all through this. Love doing that. Isn't that cool? All right, so now what I'm going to do is I'm going to do the same thing, except now I'm going to do it for the metal system. I'll use a different color so you can tell it's different. So this is for the metal system, right? Which in this case was the nut. Okay, so we're going to do the same thing, except now we're going to write everything out. So we're going to say still the same equation. So we're going to say Q. You can even write a little subscript M, letting me know it's for the metal system. This is going to be the mass times the specific heat times the change in temperature. And once again, I'm going to break this apart with my final temperature minus my initial temperature. Let me erase that one more time. Fancy T. We use fancy T's because they don't look like plus signs. All right, close the parentheses right there. We're going to do the same thing like we did before. We're going to write down all of our variables. We're going to say our Q, our mass, our specific heat, and our final temperature. So we're breaking this apart, and our initial temperature. Okay, and we're hit equals with all of this stuff. Okay, now let's go ahead and talk about this. So the mass, we would have measured that. We would have started the lab. We would have said it was something like, I don't know, let's pretend for a second that it was, they're not really big bolts. So let's say it's like, I don't know, 4.5 grams. So right, I'll do this in green. If you're red, green colorblind, I apologize already. 4.5 grams for the nut. Because it's zinc, I can't remember off the top of my head what the specific heat of zinc is, but I think it's 0.412. If it's not, then we can change our answer later on. Not that big of a deal for right now. I'm just giving you guys an example to kind of figure out how to set up your problem. Your problem's going to be a little bit different than mine because this is all made up data. I'm just kind of giving you the rundown here. All right, now on to a couple of the values that sometimes can be really difficult for students to figure out. The first one is, okay, well, we have three unknowns here. We have our Q, we have our final temperature, and we have our initial temperature. So let's go ahead and talk about these values real fast. Now, the easiest ones to figure out is actually the final temperature, because if you recall from our picture earlier, we put these two things together, right? Which means when they reach thermal equilibrium, as we discussed before, they essentially reach the same temperature. So the final temperature of the water is going to be the final temperature of the nut itself. All right. So our final temperature for our water was 47 degrees Celsius. So we're going to do the same thing. We're going to write that down for our final temperature of our water. So we're going to write 47.0 degrees Celsius, because remembering that the temperature of the bolt or the nut and the temperature of the water are going to be exactly the same thing. Okay, Mr. Dominguez, that's great. But there's still a bunch of stuff here. I still don't know Q. I still don't know initial temperature or nothing. Okay, well, we actually do know Q because remember, conservation of energy, as long as our system, right, or as close as we can, whatever the final temperature of the water is actually still going to be the final temperature of the metal, or sorry, not temperature, but the final energy that was exchanged is going to be the same, because whatever the water gained, sorry, not thermal, but the first law of thermodynamics, right? Conservation of energy says that whatever was gained by the water has to have been lost by something. So what was it lost by? It was lost by the metal. Now there's one little twist to this. Now you got to remember this. The difference is that this number, that 10,500 joules worth of energy, was lost by the metal, right? Because it heated up the water. So that means that this number isn't positive. This number is actually negative because this is the exothermic part of the system. Okay, this is where the energy came from, which means the metal lost the energy. All right, so we go back to our problem. We try to figure out what we need. Well, the only thing that we don't know is what the initial temperature of the metal is. Now, I want us to really focus on this because this is where you become a little scientist, right? And you focus on what that number actually means. So the initial temperature of the metal is actually what you heated up the metal to from the very beginning of the lab. I know what some of you guys are thinking already. You guys are already thinking, I was like, oh, wait a minute, Mr. Dominguez. So whatever the initial temperature of the metal is, right? It's going to be the same temperature as the flame. Well, that kind of makes sense, right? Over 5 minutes, it reached thermal equilibrium. At some point, there's not going to be any energy going into the metal, right? It's going to just sustain a temperature wherever it's at. It can only get so hot before it starts melting. So whatever the temperature of the flame is going to be the same temperature of the metal, which is why we left it there for 5 minutes. So that's essentially what we're going to figure out. Okay. Now, compared to some of the other manipulations or um, solving our equations, this is a little bit more difficult because now you have a subtraction sign. I had a math teacher a long time ago tell me algebra is pretty easy until you start adding and subtracting things, then it becomes hard. And it's true because all of a sudden now you got a polynomial. Those are a pain in the butt. No one likes doing those. So I'll help you out. I'll help you out with a little bit of the algebra. Even though I'm not a math teacher, I'll show you how to do it. Okay. So we still have the same equation, right? Our Q, which is our heat, times our mass, times specific heat. And we're going to break this equation again because we don't know what the change of temperature is. So we're going to say T final. Oh, that looks like an F. Too fancy with T. There we go. T final minus T initial. And it looks like, there we go. More of a minus sign. There we go. All right. So now we got to do a little bit of algebra. Once again, don't get this mixed up. That M stands for heat of the metal. So if it's confusing, I'll just erase it. Just know that I use it sometimes to figure out which system I'm talking about. So just like before, we're going to solve this the same way we solved all of our other Q problems. We're going to do a little bit of algebra, right? We're going to divide out mass. We're going to divide out specific heat, right? Because it's an equation. We already do one side, we got to do the other side. So we do it to the other side as well. Those cancel, those cancel. And what I'm left with is this T final minus T initial equals Q divided by mass times specific heat. Now we're still not isolated because I still have to get rid of this T final. Okay. So I'm going to move it over to this side. Now, the way that I do that is I got to do the opposite of what it is, which is adding it here because it's plus T final. So I'm going to subtract T final from both sides. Let's go ahead and do that. Let me erase all this junk out of the way. It doesn't think it's junk. It must think it's art. Let me erase it. Go away. There we go. Now it's gone. All right. Let's subtract T final from this side. And we subtract T final from this side. And our brand new, beautiful, wonderful, think of an adjective expression, looks like this. T initial, negative T initial, is equal to heat. Let me move this out of the way so it's not confusing for you guys. Make it a little bit smaller. I love technology sometimes. Make it smaller. There you go. Get out of the way. Cool. Q divided by, Q divided by, or heat divided by mass times specific heat minus T final. Now, some of you lazy kids will just want to leave this negative sign here, which is fine. You can do that. Just remember that whatever your answer you get over here is going to be the opposite of whatever answer is supposed to be. So basically just make whatever answer you get here, multiply it by -1, you got the answer. But rather than doing all that, we're actually gonna do the work and we're getting rid of this -1. So remember, the way to get rid of a -1, you just multiply every side to -1. When you do that, this negative will actually cancel and become positive. So to make it a little bit faster and expedient, what I'm just doing instead is just put a negative here and then make this into a plus sign. Because you got to do something, you got to do it to both sides. So our final equation that we're going to use is we're going to use this. T initial is equal to all this junk over here. Oh, let me erase this, make a different color because it's kind of confusing. Let's make it a red negative sign. That'll work better. All right, so we got all this junk over here. So all we really got to do is now my favorite thing in the whole wide world, which is to say plug and chug all of this stuff. Now my algebra, I'm going to move it out of the way because it's bugging me. So I'm running out of space here. Like small. There we go. We can still see it, right? There it is right there. There's the equation we're going to use. So now we're just going to, I think the math teacher say evaluate. Remember, I'm not a math teacher by trade. So we're going to evaluate our expression now by simply taking all our numbers and we're going to plug them in. So we got T initial. Let me zoom in a little bit. T initial. And it's equal to the negative value of Q, which is 10,500. All right, so we put 10,500. Now what's beautiful about this is because it's negative to begin with, you can see where it's going to cancel at. 10,500. So the math works out in just a bit. 500 divided by the mass of the metal, which in this case is 4.5 grams, times the specific heat of the metal, which I'm guesstimating because I forgot, 0.412. Okay, put that in parentheses and we're going to type that up in just a bit. And then we're going to add it to our final temperature, which is going to be 47 degrees. 47.0. All right, so there's our equation. Now we just got to do the hard work, which is to put it in our calculators. Now, notice right off the bat that we have a negative and a negative right here and right here. So a negative, if I may quote my favorite teacher of all time, Jaime Bustamante, a negative times a negative equals a positive. So those things cancel out. That's what we got now. So I'm gonna take my equate, my calculator, I'm gonna plug all this stuff in. And because I'm fancy, I'm gonna do it all at one time. We got 10,500 divided by that. Okay, so let's do it. Let's do it. Erase that. So 10,500 divided by, because I want this to be in a parentheses, I do it like that. And I say 45, 4.1, 4.5 times 0.412. There's too many fours. 4.5 times 0.412. Yeah. Now, the rest of it, I can do it all at one time, but I think I've never used the Apple calculator before. What if I go all the way over here? I guess it won't let me. Oh well. So I'll hit equals, and then we'll add the final temperature, or the initial temp, no, the final temperature, 47 degrees. Now, because I made up some numbers, our data is really, really crazy right now. Okay. So essentially what our experiment said, or this made up experiment that I just did, it says the temperature of our flame was 5,710 degrees Celsius. There is no way in heck that was the actual temperature of the flame. Because if that was the case, that metal would have been melted. I mean, you're probably going to get somewhere around 500 to 600 degrees Celsius. But because I made up my data, which is why we should make up our data, sometimes we get stuff like this. All right. So if I did my math, which is what I did, my initial temperature, according to my whacked out data, let's just say it's 5,000 degrees. With two sig figs, let's say 5.7 times 10 to the third degrees Celsius. And there's my answer. Box it in because I'm super proud of myself and I want to show everybody how smart I am. So there's my answer. Okay. So Like I said, this isn't a math class, this is a science class. So, like I said before, this number has to mean something. You got to figure out what that number means. So, what this number means, based on our experimental data, the temperature of our flame that we found by using conservation of energy was 5,700 degrees Celsius. Although, because I made up data, it's probably not right. But I'll leave it as is. Okay? So, that's the way that you do this kind of problem. If you have any questions, go and ask. All right, guys. See you guys later. Don't burn yourself.